Okay, so everyone can see my screen, right?
Yes.
Okay, wonderful. So we'll continue our discussion on PAC learning, and I hope this is the last lecture on PAC learning. I hope we can start learning boosting from the next lecture on. And indeed, there is one course project that's very related to boosting. After that, I will talk about generalization in neural network. As I promised that this lecture would bridge classical machine learning theory with modern machine learning. So hopefully with our understanding of generalization more theoretically, can we see what we can do for neural network, which is a very complicated hypothesis class, right? So, okay, so that's, that is just a very brief kind of introduction to what we will be covering in the next 2 weeks. Okay. So today we'll still review some of the Rademacher complexity first. I think nobody's in the waiting room, right? Okay. All right. So again, should I make someone co-host in case someone is in the waiting room? I'm gonna make Kyle co-host.
Sure. And just for the students who don't know, even if you're signed into Zoom with your UMD account, make sure you've signed in through SSO. So if you haven't, just log out of Zoom and then re-sign in through the SSO option. And then that way you don't have to go through waiting room. So for people who are currently showing up as guests, there's a handful of you. Just make sure to try to do that next time. And that way we don't have waiting rooms.
Okay, wonderful. Okay, wonderful. So let's continue our discussion on Rademacher complexity, a review of what we've learned last time. So as we already discussed, Rademacher complexity is gonna be the first complexity measure for infinite hypothesis class H. And it captures the richness of a family of function. So any function, right? It could be your loss functions, it could be your hypotheses themselves, but any family of function by measuring the degree to which a hypothesis set H can fit random noise. Okay, so something is okay. So here the empirical Rademacher complexity, just to review, is for a specific sample. So the sample is fixed. It has m examples, right? It is very important to know that the sample is fixed, and that's why it's called empirical Rademacher complexity. So the sample is fixed and you have a bounded G. So this empirical Rademacher complexity is now defined on your loss functions, your bounded loss functions, which is bounded between A and B. And also, as we said before, whenever I talk about loss functions, the family of loss functions is always associated with a specific hypothesis class H. Okay, so with this G associated with H, the empirical Rademacher complexity is defined as an expectation over the supramount of inner products of your evaluated losses on the sample and the random noise sigmas. Okay, so it's the supramount of that in expectation. All right, so as I said before, this expectation is very important because within the expectation, you can consider each of the sigmas or each of the noise as a fixed noise, right? So then there is a fixed direction. Well, so if you wanted to maximize this inner product, is basically saying you wanted to find a direction that is very aligned with that noise, and if your G is rich enough, you should be able to get such a direction. However, the thing is, you wanted to make sure that you should get a consistent high value for each of the direction in order for the empirical Rademacher complexity to be high, right? Because you have to take expectation over all realizations of the noise and the inner product of the noise with that G. right? So that's the basic idea. Now, just to recap, the interpretation is to estimate the richness of a family of functions by measuring the degree to which a hypothesis that can fit random noise using a sample S, and measures how well G correlates with random noise on S, describe the richness of G, and richer G can generate more vectors, right, on the sample S, and thus be better correlated with random noise on average. Okay. All right, so now the Rademacher complexity is essentially an expectation of empirical Rademacher complexity on samples, right? So as I said, empirical Rademacher complexity is on one sample. Now you're taking average over all the samples. So it's essentially expectation of that empirical Rademacher complexity. And so one very important concept. So we already gave you an example about how to interpret the Rademacher complexity, essentially using a very special case of a hypothesis that was either two hypotheses or one hypothesis, and these hypotheses being deterministic function. Then you should be able to calculate the so-called empirical Rademacher complexity and the Rademacher complexity. And that example has been already reviewed last lecture, but I wanted to, emphasize that that example is not a good representation of how you use Rademacher complexity or empirical Rademacher complexity. First, that is a very, very artificially made example, right? And it doesn't represent anything in practice. Also, it is a finite set. So usually in practice, the power of Rademacher complexity is for characterizing their complexity of an infinite set, okay? So, that's just an example for showing you how to understand the Rademacher complexity, and showing you how a deterministic function could have a very low Rademacher complexity, but a combination of a few different deterministic function could have a higher Rademacher complexity. And that's the only reason why we have that example. Now, coming back to generalization, since we're all talking about generalization, we're talking about sample complexity. Now, what is the generalization theory for infinite hypothesis that using Rademacher complexity? So here is one. It's not very surprising, right? We've seen these kind of forms of equations a lot recently. So Rademacher complexity bound is essentially, the theory is let G be a family of functions mapping from Z to 0, 1, right? Of course, this is associated with H, right? I didn't put that very explicit here, but since we've already made a common, since we've already said in the notations before we start these lectures is that G is always associated with H, so I'm not emphasizing that here. But one thing is very interesting here. So this is not for any G was bounded between A to B. It is between 0, 1, okay? That makes the equation much simpler, okay? So for a G, let G be a family of functions mapping from Z to 0, 1, then for any delta greater than 0, okay? So with probability at least 1 minus delta, the following holds for all G and G. So let's first see this first equation here. Okay, let me try to, again, use my pen. Okay, so expectation of G of Z. Okay, so first of all, I wanted to ask a question. What is the expectation on? Can you make a guess? Okay, I'm gonna say Z.
The random vectors?
Right. I'm gonna say Z. Do people agree with me? Yes?
Yeah.
Okay. Well, so this is actually take an expectation over Z, over the random variable Z, right? Or you can think about the underlying distribution where your data are generated from. Someone's talking about S. So Jonathan, do you want to talk about why you think it's expectation over S?
Well, I was just thinking about the Z's being drawn, S being drawn from Z,
Right.
and
Right. So
then G. Yeah.
I think you are almost right, right? Because we can also think about that way. So essentially, if you think about, there is a subtle difference here. So when you're taking expectation over Z, you're thinking that, I am basically averaging over every single examples that are drawn from an underlying distribution. Think about that way. But when you're taking expectation over the S, so basically you will have a function that is dependent on S. Okay, so some function that's evaluated on the entire M examples in that S. So, you have some function within the expectation, and then expectation over S means just that, you evaluate this function on a set of S, or on one sample S, then you evaluate that on another sample S, and you do that for infinite amount of times where, the samples are all sampled from R to the power M, D to the power M, right? D is the distribution of the Z, so D to the power M, meaning like you have M such jaws. Well, so you just take an average over, infinite jaws of such S, and that's gonna be your expectation. Does that make sense? So there is a little subtle difference there.
Thanks.
Okay, right. So the expectation of GZ, which is gonna be, smaller than equal to this. So what is this? Summation of G of Zi. So Zi are just your training examples. So it is your empirical average of the function, right? Because G of Zi is gonna be one empirical estimation, on one example in your training sample, right? And this 1 over M is just, in weight, so it's like average. Now, so what is the difference? Right now you can see this seems to be, the difference between these two seems to hint that this is a gap between the true error and the empirical error, if you think about G as a loss function, right? Okay, if there's no objection, I'm gonna assume that that's a yes. Now, so we're saying that this thing, this true error is gonna be smaller than equal to the empirical error plus 2 times the Rademacher complexity of the entire family of function G, right? So remember, notice that this is family of function G, right? Because our Rademacher complexity definition is on a family. Also, it is on M, so the Rademacher complexity of M examples, right? Not M plus 1 or M minus 1 or anything else, right? Now there is another term, which is the logarithm, square root of logarithm 1 over delta divided by 2M. Okay, M is the number of examples in your sample. Again, delta is just your probability variable. Okay, so is this interpretation clear? So this first equation is just telling you with high probability, the true error and the empirical error will be different by this amount. Okay, and this amount is definitely you can think about it as generalization gap, right? If G is your loss function. So this generalization gap apparently depends on Rm of G and this term, which is you've already seen it a lot, even in the finite hypothesis class, setting. You've seen this term a lot. Now, the second term is different only in the sense that you've replaced RMG with RSG here. But now this term also has been changed a little bit, right? So basically this means that your RSG, how to say this? So basically it's like this term has been replaced by by this term. Okay, so basically this means there is a difference between the Rademacher complexity and the empirical Rademacher complexity. Okay, all right, so I don't have time to go through the proof of the theorem in class, but I'll provide you some hint or some basic like guidance in understanding the proof. But first, I wanted to emphasize that interpretation of expectation of GZ, sometimes you can think about it as R of H and take an expectation over H. Right? Can you do that? Oh, that's a bad notation here. So it's not expectation over H, but it's just yeah, do you see why? So yeah, so a small g is corresponding to a small h, right? So now this is taking expectation over g of z, okay? So this is a bad notation. I'm making a mistake here, right? So g is corresponding to h, and this expectation of g of z is for a specific g, right? I'm not taking average over the g here. So what this corresponding to is essentially R of H of, essentially it's just R of H because it's the definition of R of H is already the true error of, what happened? Yeah, the definition of, sorry, what's going on here? I don't know why I cannot erase this, okay. Okay, so it's already R of H. Do you see that? Because R of H is already the true error, it's already taking expectation over the random variables that your H is evaluated on. So,
can I ask, what was G again?
G is the loss function associated with H. So, if you have a specific fixed loss function, let's say 0, 1, for example, 0, 1 loss, or maybe hinge loss, or like cross entropy loss, right? And so on. So let's denote that as an L. So I'm just reviewing what we've already talked about in the notations page. So now the G just means that, it is like G has to be associated with a small h. So it just means that L of H of G of Z just means L of HX, Y.
So is that arrow there an equal sign? The expectation of G, is that equal to R of H?
Yeah.
Okay, thanks.
Yeah, I made a mistake at the beginning, right? I said this is expectation of R of H, which is not true. Okay, so the definition of the G is just this one.
That might be true if you
also take expectation over G, right?
Yes.
Okay, so, right. So here, specifically, we are, we're not taking expectation over G here. This is only taking expectation over Z, okay? Whereas, therefore, this G expectation of Z of GZ is gonna be equal to this R of H, where H is corresponding to the G here. All right? Does it make sense now? All right, so one thing I wanted to really emphasize is that the Rademacher complexity is distribution dependent and is also data independent. What do I mean, right? So this Rademacher, this Rademacher complexity is distribution dependent only because when you evaluate when you are evaluating the empirical Rademacher complexity and then take an expectation over that, you're kind of counting for like the underlying distribution of the data, right? If you recall that definition. So maybe this is a little bit unclear. Let me go back to the definition of the empirical Rademacher complexity, because Rademacher complexity is just taking expectation. Okay, so the empirical Rademacher complexity is for a specific S here, right? It is a function over S. And now, if you take the expectation over S, then there is already an underlying distribution of the S, which is d to the power m, which is already considered, right? So if you have a different d to the power m, your Rademacher complexity will be different, right? So that's why it is a distribution dependent complexity measure. But it's data independent. What do I mean by that? Like it is not specific on a training data example, or training data sample. It is not specific to a training data sample, right? It only requires that your training data has m examples, but it doesn't require I have to use this specific training sample, right? So that's why it's called a data independent. Whereas empirical Rademacher complexity definitely is distribution dependent, but it's data dependent because it is a function of S. Depends on the specific S you choose. Okay? So that's the interpretation here. Any questions, comments?
Can you swap the order of the expectations?
Which one are you thinking?
So R of G equals expectation over S, and then of expectation over sigma, and then there's something in there. Can you swap the order of those expectations?
Oh, so you're saying in terms of defining Rademacher complexity, so here. So, okay, maybe this slide is easier. So you're saying in this notation, you are taking expectation over S at the outside loop, whereas in the inside loop, you have the expectation over sigma.
Right.
That is a very good point.
Because these are just integrals, so you're like switching the order of two integrals, and sometimes you can do that.
Yeah. Yeah, I don't think there's a reason you cannot do it. Actually, I think you should be able to do it. Anyone has a comment? Do you understand the question? So Michael, right? Michael is asking, right now, the definition is of Rademacher complexity is this one, right? Right? So he's just asking, can we just switch the order of the expectation and just do this? My answer is yes, although it's hard to interpret what you are calculating within the inside, in the inner bracket. So basically, my question is, what are we calculating here? Is there any physical meaning associated with this expectation? Right, so it seems like here, what I'm highlighting was in the blue box. Here is the expectation over S, right? And then supremum of a fixed noise. Inner product was the evaluation of the losses on this S. Okay, so you're saying that I'm taking the supremum of the inner product between a fixed noise and all possible evaluation of the evaluation of the losses on a lot of samples, right? Which I don't know how to interpret it. Mm-hmm.
So I think in terms of the first one, it tells us like the inner expectation tells us how well we can fit random noise, but in the second one, it's like given a fixed set of a fixed noise vector, how well it can fit that specific noise, giving distribution of samples, which I think is maybe not as useful as the first formulation.
Yeah, so the interpretation is fine, right? It is like, we know that this just means that, if it was a fixed noise, you are evaluating this G. Actually, this is a function over S, right? Because you are evaluating G, Z1, G, Z2, G, ZM, right? You are evaluating all these terms on a specific S, because the Z1 through ZM is just in S. Right? These are just in S. So however, I just don't know why we need that quantity, or why does that help us in terms of understanding the complexity of the hypothesis class. Okay? So yeah, mathematically it's fine. It's just this way, the way that we are defining as the empirical Rademacher complexity is physically more meaningful. Okay, good discussion here. All right. So I'm gonna, omit the proof. My original plan was to go through the proof, but I think since, I've spent a lot of time reviewing inequalities, union bands, convexities, Jensen's inequality, so I think maybe you guys should go through the proof yourself, and if in case you have questions, you can have a discussion with your peers. So just a few important bullet points I wanted to mention. So in this proof, a very important thing you are going to use is the McDiarmid's inequality, right? This is function from random variable section. We will learn the concentration inequality, right? So this one we've already learned. Now, Jensen's inequality we'll also be very familiar with. Also, one of the important things that's going to use in this proof is the convexity of the supremum of convex functions. So that's also something to keep in mind when you read the proof. Now, another important point is that changing one point of S, meaning changing one example in sample S, will make actually will make Rs of G vary by at most 1 over M. So making the Rademacher complexity vary, sorry, empirical Rademacher complexity vary by at most 1 over M. So this can also be examined, and it is a very important fact to be used in the proof. And then finally, just like, you know, every generalization theory we've seen, we need a union bound, just so that it applies for every H within capital H, okay? All right, so that is what we need to say. Now, as I already hinted that we've been talking about the Rademacher complexity of loss functions G all the time. You know, sometimes we just want to directly characterize the Rademacher complexity for hypothesis that H. So can we do that? Yeah, actually we can, and there is a very interesting relationship between G and H, as long as H be a family of function taking values from -1 plus 1. Of course, for other H's taking values other than -1 H1, you should be also able to get a relationship. Usually the relationship between RMG and RMH is a constant factor difference, okay? So sometimes for complexity theory, you can just ignore them because you care about the order anyway. So let H be a family of functions taking values in -1 plus 1. Let G be a family of 0, 1 loss functions of H. So basically means G is gonna be, you know, mapping the collection of H such that it so G is gonna be the map from X, Y to indicator function of whether HX equal to Y. Okay, so it's a 0, 1 loss, but it's a collection of the 0, 1 loss on every H. So you can see this notation is very important. Is the collection of these loss functions for every H. Okay, so that gives you the G here. Now the Rademacher complexity of the G on M example is gonna be half of the Rademacher complexity of H. And the proof is rather simple. You know, since it's rather simple, I just put it here. So the Rademacher complexity of G, okay, so G is being like, you know, the loss functions, the family of loss functions, 0, 1 loss functions. You know, based on definition is just expectation of S, sigma, superma 1 over M, summation of the sigma. This is just the inner product between the sigma and the loss function, right? So I'm just writing out the element-wise notation of the inner product. So summing up of the multiplications, element-wise multiplications. Now you can see that this step is nothing but making the change here. We know that this indicator function can be written as half of 1 minus yi hxi. The reason is yi can only take values -1 or 1. Okay, so when yi is -1 and hxi is also -1, then what would this be? This will be 1 minus 1. It's going to be 0. So you would have a 0 error. So this is okay. Or when yi is -1 and hxi is +1, so this will be 1 plus 1, but with a half at the beginning. So it's going to be 1, right? So you can see this is the same as this indicator function here. And this is used a lot, you know, in learning theory, especially for functions taking value from -1 and 1. Okay. All right. So from this step to the next step, what you're doing is just to take the make an arrangement of the variables, right? So it essentially becomes the supermon of 1 over m summation of minus sigma I yi h xi. Any questions here? step is very obvious. Okay, so lastly, the last step. So I wanted to ask why I can just take the minus out, or essentially I can just cancel the minus sign. Why can I do that? Yes, yeah, exactly. Because the sigma I can take values either +1 or -1 with half probability or equal probability. So whether you put a minus sign ahead or not doesn't really matter, right? So it doesn't affect the final result. So that's why you can just ignore the minus sign. And essentially what this is just the definition of Rm of H, okay?
Is yi missing purposefully in that last step? Or are you like taking out minus and yi?
Right, so also yi disappeared. Why is that? That's a very good question. Why do I have yi out? Actually, that's a very good question. Yeah, I wanted to. So, actually, I think this is a good time for a discussion. Do you want to have a discussion? Why can I just take yi out? Do you want to do a breakout room discussion? Okay, I'll do that. How do I do breakout room? Okay. I think someone is alone in breakout room 9. So for those of you who are not in breakout rooms, please join the breakout room so that people are not alone. Breakout room 9 has only one person there.
Rademacher complexity of H.
Yeah, which is going to tell you, I guess, the richness of it, of the hypothesis.
Oh, I'm on mute. Sorry. Okay. Any thoughts on why, any thoughts on why we can ignore yi? Any, fruitful discussion?
Because sigma I will always be negative of yi. No, if yi is 1, then sigma I will be -1. And if yi is -1, then it will be 1. Yeah, so they will cancel out each other's effect.
Yes, exactly. You're absolutely right? So basically, because of the sigma is only taking value from -1 or 1, all right? So whenever y is -1 or +1, it doesn't affect the result because it will just merge away, right, with the signs of the sigma. So that's why it is very powerful to have such Rademacher variables. Okay, so it can basically ignore the signs associated with it, multiplied with it. And it's very important to notice, yes, Joy was mentioning everyone, or it's emphasizing that it's very important to notice that yi can only take values -1 or 1. So it's a sign variable, basically. You can think of it, right? So that's why you can just ignore it. If yi is just 0 and 1, then that's another story, okay? All right, wonderful. I hope you've seen, you've talked with your peers and you had a little bit of chance of chat to each other. So now, as I said, the generalization error on Rademacher complexity of empirical and empirical Rademacher complexity, because we've established the relationship between G and H. So then I can just write the generalization bound as the following. So it's gonna be the probability of the generalization gap being RMH, and square root of logarithm 1 over delta 2m is the gap being smaller than that is with high probability, greater than 1 minus delta, okay? So that's like, you can think about this gap as the generalization gap here. Now, with this relationship between RMG and RMH, you're also able to relate the generalization bound using the empirical Rademacher complexity of the H. So you can see again, the generalization gap is, smaller than the empirical Rademacher complexity of H plus 3, square root of logarithm 2 over delta over 2m. Okay. All right. So now we've basically find a bound that is distribution dependent for generalization bounds. So that's the first one, or the second one, which is a data dependent bound for generalization bound. Okay. So in a lot of scenarios, generalization bound is data independent, but this one is data dependent. And in a lot of cases, generalization bound is distribution independent, but now this bound is distribution dependent. Now, why does that make them attractive, right? So because if you have this dependence with data or distribution, you might be able to get a tighter generalization error, right? Because just imagine, you might have some data distribution that is really, really like a worst scenario, but somehow your generalization gap has to cover that worst scenario. Whereas this distribution dependent or data dependent bound, you could just work on the scenarios that you see rather than something that is a worst scenario, but you don't necessarily see a lot, okay? So that is why this distribution dependent and data dependent bounds are very desirable. However, the bad news is that characterizing the Rademacher complexity and the empirical Rademacher complexity is very, very challenging. Okay, so that's why people have done experiments to estimate them, to approximate them, but you cannot do that, right? Because this is, if you're just approximating that, then you would need another concentration bound, which would make things not very reliable. So, there are some pros and cons, as we've discussed at the beginning of, the lecture, actually last lecture, about the infinite hypothesis set. So for this Rademacher complexity, it's very desirable in terms of it's pretty tight, but it's less desirable because it's computationally expensive to compute. Okay. All right, so finally, let's have a comparison with finite H. Now that we've learned the first generalization bound for infinite H, right, using Rademacher complexity. So just to compare the generalization gap between the finite H and the infinite H, right? So on the left-hand side is infinite H and right-hand side is the finite H. And I'm using also, I'm listing both the consistent case and inconsistent case on the right-hand side for finite H. But now let's look at the inconsistent case, right? So it's basically saying, oh, did I make a mistake here? I think I forgot a square root here for this inconsistent scenario. Okay, I have to change that. So don't trust this equation here. So just refer to the previous slides of our inconsistent finite H. So I think I've made a mistake here. There is a typo. But nonetheless, when you compare them, you can see the RH, the RMH, the Rademacher complexity, and the RSH, the empirical Rademacher complexity basically serves as something very related to the cardinality of H divided, logarithm of cardinality of H divided by M, right? Some kind of that rule, okay? That's, the kind of insight I wanted to provide here. Okay. All right, so again, I will make the change here. I think there is a typo here. The consistent and inconsistent case shouldn't have the same generalization gap, right? Generalization gap is a square root factor different. So, so I think there is a typo here. Okay. Now we've learned about Rademacher complexity. So a natural question is, how do we compute the empirical Rademacher complexity? Indeed, it is very difficult. It resolves basically computing this, expectation of sigma supremum of 1/m, the inner product between noise and the hypothesis, requires solving ERM problem, empirical risk minimization problem, typically computationally very difficult. Now, the natural question is, can we relate this data dependent and distribution dependent complexity with some combinatorial measures. And essentially, can these combinatorial measures be easier to compute, right? So that brings us to this growth function, okay? So growth function is gonna be the second complexity measure that we use, which is a combinatorial metric that we use to measure the complexity of the hypothesis set or fit of infinite hypothesis set, okay? So now growth function is defined as the following. It's gonna be written as pi subscript h. So pi sub h, it is mapping from integer to another integer. What does this mean? It's just that it's defined as the maximum number of ways that any m points can be classified using h. Okay, so now you have m points in your data examples. Okay, so then what is the maximum number of ways that m can be classified using h? So if h is rich enough, then you can imagine this is going to be 2 to the power of m, right? Agree? Why? So if you don't say that m points can be classified using h, just say if you have m points and m can be, each labeled as -1 or +1, so what is the maximum number of ways you can mark the m examples? It's just 2 to the power m, right? Because you can either put a -1 or +1 for that example. So it's 2 to the power m. Now, the question here is that the growth function is not only saying, how many possible ways of labeling them. It's just, also it's like the maximum number of ways of labeling these m points using h. So for example, let's consider the most extreme case that your h has only one hypothesis, which is a deterministic function, always mapping everything to -1. So what is the maximum number of ways that any m points can be classified in this scenario? Yes, exactly. It's going to be 1, because you were always going to mark everything you see as -1. So overall, it's going to just be one way of labeling these m points, right? Because I have a deterministic function in my h. Of course, I'm talking about infinite h here, so that's not a valid example, but you get what I'm saying. Okay, so now you can see mathematically it just means that the definition is just the pi sub hm. As I said, this maps from input to another input. So m is the input integer here. So it's just number of points you have. So it's just the maximum over any points x1, xm within your input space. You have the collection of this is a vector. So let me use my pen again. This is a vector, right? Right. So you can think about it as like a way of how to labeling these m examples, right? So h of x1 is just one way of labeling x1. H of xm is just one way of labeling xm. Now, in the collection is just, one way using h is the one way of labeling all the m examples. But now you are looking at the collection for every possible h within capital H. So this basically means, don't forget there is a cardinality sign here. So that means it's the maximum number of ways that m points can be classified using h. Okay? So the cardinality is very important. It's kind of easy to ignore. All right? Right, so the maximum is over the m points. Okay? Now you might wonder, this seems to be something that's a little bit more intuitive than empirical Rademacher complexity or Rademacher complexity, but it seems to be still rather difficult to compute, right? For example, how do I list all the H within my capital H? I have an infinite set, right? That's one question. Then the second question is, of course, I need to compute the cardinality, but this cardinality is maximized over all possible samples, all right? So what I mean is like, you're kind of selecting such a sample as x1 to xm, such that your H can create the most possible ways of labeling on this sample. So that seems to be also very difficult, right? Because any sample could be a candidate and you can't just check every sample here, okay? So now do you see the difficulty here? Seems to be very easy to understand concept. It's just a maximal way of labeling these M examples using my H. But indeed, because of the infinite number of examples or uncountability of the H is very hard. Also, this is maximized over a sample, which is also very difficult to compute. Okay? Any questions so far? All right, so now with this, I'm gonna say that the following. So I will not prove the following, but this is something is worth mentioning in class. So let H be the family of functions taking values from -1 or 1. Then the growth function bound on RC. So what this means is that this RC, so this is Rademacher complexity, RMH, it's gonna be smaller than 2 logarithm of the growth function divided by m. So indeed, it's somehow a lower bound of a function of the growth function, right? So it is not exactly like the lower bound between the Rademacher complexity and the growth function, but it's some other form of the growth function. So indeed, you get this property here. And this somehow show you that the growth function is a looser bound than Rademacher complexity because it is not data dependent or distribution dependent. Okay? It is purely combinatorial. All right. So what about the generalization bound of this? So, very similarly, you will get a similar generalization bound, basically because you have a lower bound, an upper bound of the Rademacher complexity. So you just replace the Rademacher complexity with this term here. And that's why you have this right here. Okay. Yeah, so if you know the generalization bound of the Rademacher complexity, because of this relationship, it is easy to get this bound. Okay?
I have a question.
Yes.
So here we are calculating the number of ways in which endpoints can be classified using H, right? So within this braces,
yes,
if you see, like if we select one H, then for that H, given an input, there can be only one, like for a fixed H, there can be only one output, right?
yes, that's true. There can only be one out. Yeah.
So each hypothesis will, each hypothesis will give me only one way of classifying endpoints.
Yes, exactly.
So this is basically, so what this value, I'm a bit confused.
Okay, so the thing is H, you have infinite many of such H, right?
Right.
So can I say that, I just have a infinite growth function? Do you see what I mean?
Mm-hmm.
So the point is that some of the H will have the same way of labeling. You know, there might be a collection of H. I don't know, right? Or it could be like infinite number of them, but within some range. Do you see? So like maybe, let's say H1 was in H. That would map. So for any H was in H1, it would always map this into the same thing.
Mm-hmm.
Right? So that's possible, but it's very difficult to find such a H1. And it's also difficult to find how many such HIs you can find to map it into a different labeling of the endpoints.
Okay.
Question on that. Could this be infinite?
No, so as I said, pi of HM has to be smaller than 2 to the power m. Because you are looking at H, what did I do? Oh, okay. So you're looking at H taking values. So your H can take values only from -1 or +1. So what I mean, oh, did I erase everything? Sorry. Okay, so
Okay, that makes sense.
HM has to be smaller than equal to 2 power m.
I have a question too. So
Yes.
if H had a finite, like if the cardinality of H was finite, or like if it wasn't infinite, then the growth function would be equal to the minimum of 2 to the m and the cardinality of H, right?
That's not necessarily true, right? For example, if I have finite H, although this doesn't apply here because H has to be infinite, if I have finite H, I could have many different H's, but these H's could potentially give me the same result, right?
Okay,
So it depends
see
on the
now.
richness of the H again.
Yeah. Okay,
Right.
that makes sense.
Yeah. Does that make sense? So any other questions?
Oh wait, can we say that it's bounded by the cardinality of H if it's finite?
I think that's fair, but you know, like I said, that's not a valid argument because you know, in this scenario, this is the growth function is only defined for infinite H.
Okay.
Okay. Well, so now, as I already said, the problem is that computing growth function is difficult. So it is also very, very difficult. Now, the solution is the VC dimension. And a lot of you have learned about VC dimension. And finally, I think I'm giving you like a history of how we come up with VC dimension. Okay, so VC dimension definition, a lot of you have seen that before. So the VC dimension of H is defined as the size of the largest set that can be fully shattered by H. So what do I mean by shattered? Okay, so shattering means a set of S, you know, of course, greater than 1 points, right? It's said to be shattered by a hypothesis H when H can realize all possible ways of labeling the points. Does that make sense? So basically, H is rich enough to label the m points in any ways. So basically, with H, you're able to label the points in 2 to the power m ways. Notice that this m is for a specific m, right? It's not for anything. It's for a specific m. So its shattering just means that the H can realize all possible ways of labeling the points of S, where the S is size m, okay? Does that make sense? Or that's a little bit confusing. So let me, emphasize this formal expression here. So what does this mean? So first of all, pi h of m equals to 2m. Do people understand this? So notice this pi h of m is just the growth function. Okay, so what does this mean? This means that with my hypothesis set, you know, on a sample S with m examples, my hypothesis H is able to realize any possible ways of labeling these m examples. Okay, so that's what we mean by pi h of m equals to 2 to the power m. Okay? And what is this really saying? This is really saying that I'm trying to characterize the complexity of a hypothesis, which is infinite, through the complexity, through how rich it can label a finite data set sample. Okay? So, you know, you have this infinite set that you don't know how to measure, but you kind of measure it through like this finite sample, right? How do you measure through the finite sample? It's through, you know, whether your hypothesis is able to generate a rich labeling of this finite sample. Okay, so that's the real, you know, I think intuition behind this, right? So now what is M? Well, sorry. Oh, this is a typo, right? This is terrible. Okay, sorry about that. I'm saying pi h of m is the maximum. So this is definitely a very foolish typo. So this is VC dimension of m is just defined as the maximum of such an m, such that, you know, the growth function is 2 to the power m. Does this make sense? So this basically means that this VC dimension is, you know, if I have a very small sample, okay, the sample have m, and m is m examples, and m is really small, you know, because I only have a very small sample, you know, although my hypothesis is not really rich, but I should still be able to label, you know, the points in all possible ways. However, when I have more and more examples in my sample, because my hypothesis set is not that rich, so I cannot realize all possible ways of labeling all these examples. Okay, so then the definition of the VC dimension is the maximum number of examples in a sample that you're able to label them in every possible ways. Does this make sense? Yes, yes, this is specifically defined as, you know, 2 types of labels, but you could, you know, easily realize this to like multiple types of labels. Then it's just be, instead of 2 to the power m, it's gonna be like, you know, c to the power m, where c is the number of label or types of labels, right? Okay, so any questions? Sorry about the typo here. So this is the left-hand side of the equation is VC dimension definition. And this is the obvious typo here. Okay. So shattering basically is just the set is set to be shattered by a hypothesis set when H can realize all possible ways of labeling the points. And actually a possible way of labeling a possible way of labeling all the points is called a dichotomy. Okay, so all possible ways of labeling the points is called, like, you know, all dichotomies, right? So it's just a fancy name for a way of labeling the points. Okay, so if the VC dimension of H is D, Yeah, sorry. Here I should say VC dimension of H. Yeah. Again. So it's the VC dimension of H. Okay, sorry, yeah, not M. So if the VC dimension of H is D, right? So then there exists a set of size D that can be fully shattered by H. Notice that this is a existence. There exists a set of size D that can be fully shattered by H. Okay, so this is very important. You know, basically, I wanted to say, is it fair to say all sets of size D or less are fully shattered by H? If I know, you know, so if I have a VC dimension H equals to D, okay? So my question is this argument correct? With all sides of, oh, it's already. Okay, so let me finish this slide, and you know, we can leave the few examples to the next lecture. But I wanted to have a final discussion about whether this argument is correct or not, right? So do you think it's correct? Do you want it to vote? Actually, I think you can use your Zoom to vote. You can do a thumb up if you think it's correct, or thumbs down if you think it's incorrect. And that is very crucial for understanding the, you know, characterization of VC dimension. I would say the most important thing here. So do you want it to do a thumbs up or thumbs down? No? Okay, maybe people are, okay, so I see a lot of thumbs down, but also a lot of, I guess, uncertain here, right? So indeed it's wrong, and this is a, you know, very important point I wanted to make here. Okay, so it is talking about existence. If there exists a set of size D that can be fully shattered by H, then you can see its VC dimension is D. But doesn't mean that every set, you know, every training set or every sample of size D can be shattered by this H. Okay, so therefore, because of this argument being wrong, then what we can do to compute VC dimension is just finding a lower and upper bound. So I won't be talking about the lower and upper bound today, but I want you to go back and think about this question, and we can continue the discussion next week. Okay, thanks everyone. Also, don't forget to read your textbook on Adder Boost before we begin the lecture next time.
Thank you.
Thank you.